we're going to take a look at some linear transformations in this problem and determine if they are one-to-one linear transformations. So one-to-one is a certain property that a linear transformation can have or not have. In part A, we're going to work with a linear transformation that has a matrix representation of the following. It's defined as the matrix A equals this matrix right here. And we are going to determine, is this linear transformation one-to-one? So that's the question that we need to answer. Looking at this linear transformation, what we need to determine, really, for it to be one-to-one, is this linear transformation comprised of a matrix that has linearly independent columns? If it has linearly independent columns, then we know that this linear transformation is one-to-one. That's how you check if a linear transformation is one-to-one. If it has linearly independent columns, it is one-to-one. If it has linearly dependent columns, it is not one-to-one. So we've already looked at this before. So like I said, if it is, the answer to this question is yes, it is one-to-one. If the answer to the question is no, then it is not one-to-one. So now what we need to do is figure out, are these columns linearly independent? So how do we do that? Well, we can do that by solving an augmented matrix. If this augmented matrix has only the trivial solution, then we know they're linearly independent. If this augmented matrix of this homogeneous system of equations has many solutions to AX equals 0, then we know that the columns are dependent. So really what it boils down to is being able to solve this system of equations. So we form the augmented matrix. Now I'm going to go ahead and do row reduction. We're not going to go through all the details, but we'll end up with this row-reduced matrix for the augmented matrix. Looking at this, what do we see? We see that there's only one solution. x3 has to be equal to 0, x2 has to be equal to 0, x1 has to be equal to 0, so we only have the trivial solution. Since there's only a trivial solution, that means the columns are independent, and since the columns are independent, that means that this is a one-to-one linear transformation. Let's work another example. I'm going to change things just slightly. So I'm going to write down the exact matrix we started with, but right here, this entry, I'm going to change that just a little. Let's change that to be equal to 3. So we've made just one change to our matrix. And we're going to ask ourselves the same question. Is this linear transformation one-to-one? That's the same thing as asking, are the columns of the matrix linearly independent? If the columns are linearly independent, then we know that this transformation is one-to-one. And if they're dependent, we know that it's not one-to-one. So again, we form the augmented matrix for the homogeneous system of equations. Everything is equal to 0. We perform row reductions, and we will end up with this row-reduced augmented matrix. We end up with this. This is quite a bit different than the part A problem that we worked, even though we only changed one entry in the matrix. We have this column right here, which says that we have a free variable. That means there is an infinite number of solutions to the system of equations that we just solved. So there's an infinite number of solutions, not just the trivial solution. So since there's not just the trivial solution, that means that these columns are linearly dependent. Since they're linearly dependent, that means that our linear transformation is not one-to-one. So there's two examples of determining if a linear transformation is one-to-one, given its matrix representation. Checking one-to-one really boils down to checking the linear dependence of the columns. To check the linear dependence, we form an augmented matrix corresponding to a homogeneous system of equations, and we solve it. If we get just the trivial solution, that means the columns are independent, which means the transformation is one-to-one. If we solve it and get more than just the trivial solution, that means the columns are dependent and the linear transformation is not one-to-one.